The crushed stone aggregate is used as loose bed foundation for highways, airport runways, and railways. And it's mixed with a cement sand matrix to form concrete for dam and building construction and highway and runway surfaces. It's also mixed with asphalt to form asphalt concrete, constructing highways and runways. The types of crushed aggregate commonly used are pictured here. Top left is granite, to the right gravel, bottom left limestone, and slag. Here we're showing views of an image file display from a three-dimensional automated image analyzer on both so-called coarse and fine aggregate. More on the method later, but each row consists of different random projected digital images of one particle as it drops through the sensing zone. The top two are coarse aggregate, with the images sorted by thickness on the left. 30 millimeters was the largest thickness, and on the right, 69 millimeters was the largest length. On the bottom, for fine aggregates, the largest thickness was 8 millimeters and the largest length 17 millimeters. The complete image files can be displayed by scrolling, and they can be printed. Both the 2D and 3D parameter values for any particle selected in the file are listed in the upper right corner. The aggregate mining process consists initially of dozers removing the overburden, and then holes are drilled, packed with explosives, and blasted. Trucks take the rocks to the crushing plant, where their size reduced in common crushers like these: jaw, gyratory, cone, compound, impactors, and roll crushers. Then vibrating screens sort and separate the rock into various sizes. Some stones will be washed with water to clean so they can be used in cement and other construction mixes. Washing removes fine grains of sand, clay, and dirt. They're then hauled by truck to stockpiles, where loaders move product for shipment. There are a number of preferred and geometrical or morphological sizes and shapes for construction aggregate. There are published required size distributions per specific regional testing standards followed, and this affects packing density and general strength and wear of the mixes used in construction. They should be unidimensional rather than flat or elongated, which affects load-bearing strength. They should have angular rather than rounded surfaces, which affects internal holding friction in the bed. They should have high roughness rather than smooth surfaces, which affects wear resistance and binding property. Finally, they should have high surface area, which affects binding and overall mix strength. The manual testing now performed in this industry to measure the required parameters are very antiquated and take a very long time to complete. And in some cases, we've heard that it takes to the point that they only get run on a weekly basis. There are three major standards organizations that have published standards for aggregate tests: the US, Europe, and India. ASTM standards D4791 and 5821 for the US, the British standard BS-EN 933-3 for Europe, and IS 2386-1 for India. The ASTM standards include flat elongated and fractured particles, which correlates with angularity. The British and Indian standards cover flakiness index, a value similar to the ASTM 4791 parameter, because it's an indication of general strength of the final highway bed, plus for the Indian standard Angularity by manual voids measurement and elongation, which correlates with the flat elongated parameters in ASTM 4791. And all three standards list their own but very similar required size distributions as measured on standard sieve size parameters. Additional aggregates parameters are being evaluated and in some cases used by industry include surface roughness, surface area, and sizes for all three major axis dimensions, length, width, and thickness. Surface roughness can be an indicator of wear resistance when measured before and after skid tests. Surface area is an indicator of bonding or binding strength within the cement or asphalt matrix. And the product of three-dimensional length, width, and thickness measurements can be a true measure of volume distributions. Aggregate certified standards measure load-bearing strength as flat elongated parameters in ASTM D4791 or flakiness index in the British and Indian standards. Angularity as an indicator of fractured faces and sharp angles is from ASTM 5821. Elongation, like elongated, is from the Indian standard. All the parameters in the three standards discussed can be measured by 3D image analysis. And here are four more parameters being evaluated and in some cases used as calculated from image analysis measurements. Surface roughness is the degree of roughness or jaggedness of particles' surface. This near spherical particle diagram would have a high surface roughness. Three parameters describe roughness quantitatively. Convexity on a scale of 0 to 1, a lower number being a rougher surface. Solidity, similar to convexity, and concavity, where a higher number would mean a rougher surface. Surface area of that same image would simply be the area of the image in square microns or millimeters. Length, width, and thicknesses are straightforward, and angularity is a quantitative measurement of the degree of acuteness of angles on the particle. The two images taken from the file show particles with angularities of 19 and 27 respectively, with the higher number representing a more angular particle. The flat elongated parameters per ASTM 4791 are different for conventional mixes and the new superpave mix being adopted in many areas. The hand calipers used for conventional mixes utilize more dimensional measurements and at more ratios than required for superpave. But either can be measured and calculated using automated 3D image analysis. Disadvantages of caliper measurements of flat elongated parameters: very time consuming. Measurement can take up to 1 day with a skilled technician. They're error prone, subject to operator interpretation, transcription, and calculation, and small unrepresentative samples are usually used. The flakiness manual test consists of a series of screening operations per the British standard. First, the sample is screened on a series of square-hole screens, followed by a series of bar screens. See diagrams above for screen sizes. Each square screen fraction staying on the screen is then screened on a bar screen with an opening about half the interval of the square screen fraction. The sum of bar screen's undersized mass divided by the total mass to the square screens times 100 is the total sample flakiness index. The flakiness index for each individual sieve is the mass of the bar screen undersize minus 40 millimeters in the above example with the red arrow, divided by the mass in square screen fraction feed 80 by 63 millimeters in this example times 100. Flakiness index is obviously on a scale of 1 to 100%. The higher the flakiness index, the flakier or weaker the stone mix is. For the Indian standard, flakiness index is measured manually on a handheld slotted gauge for length and thickness measurements. Disadvantages of traditional flakiness index measurement: difficult manual sampling labor, time-consuming screening operations, and error-prone weighing up to 26 heavy screen fractions, measurement, transcription, and calculation of data. Fractured particles per ASTM 5821. A face is considered fractured if it has a projected area at least as large as 1/4 of the maximum cross-sectional area of the particle. A fractured particle is considered to have 1 or 2 fractured surfaces. To conduct a test, a technician visually inspects a sample for 1 or 2 fractured surfaces, measuring the sample twice for each category, then calculating and recording the percent by mass or number, which have 1 and 2 fractured surfaces. Disadvantages of fractured particles: technician subjectivity. This is a very subjective test with a high chance of different technicians coming to wide differences in results. Error-prone in visual judgment, counting, recording, and calculating results. And it's a very slow process. It's run on, again, a very small, unrepresentative sample. This illustrates how the three-dimensional mode of dynamic image analysis works. The digital camera tracks the tumbling, rotating orientations of each particle, and from those multiple individual images calculates maximum and minimum parameters so that all 3 axes are calculated. This is a short video we've been given to use, which illustrates a live measurement being made on a PartAn 3D Maxi at an aggregates plant in Norway. It starts showing the system where a technician is working. Then it pans to a view of it making a measurement, which includes a view inside the instrument itself where the sample is falling through the sensing zone. Particles tumbling through the sensing zone, vibrating tray feeding the feed to the analyzer. And you can see again the tumbling particles and the strobe light photography. Advantages of three-dimensional image analysis. The PartAn 3D image analyzer measures in the three-dimensional mode for additional parameter reporting and much more accurate results for all parameters. 3D image analysis is available, patented, from only Microtrac. First, the third dimension, thickness, is measured in addition to length and width. Thickness is a very important parameter to measure for flat particle types. The smallest width observed in a series of images of one particle tumbling through the sensing zone is assigned as the 3D thickness parameter for that particle. And the largest length and width observed in these images are assigned the 3D length and width values. This then allows calculation of such unique parameters as sieve parameter, a function of thickness and width, length over thickness, width over thickness, length over width ratios, and flakiness index, all for the aggregates application. And much more accurate size measurements can be made when considering all three dimensions rather than only two. This means that shape measurements are also more accurate, as most of them are calculated from ratios of size measurements. And in 3D mode, individual particle volumes can be calculated as the product of length, width, and thickness, giving a volume distribution that isn't dependent on particle shape or orientation, as is the calculation of equivalent spherical diameter reported as a volume distribution. Here is one of several results displays in the PartAn 3D mode software. Notice in the graph and table windows, top left and right, that not only are the length and width size dimensions displayed as they are in 2D analysis, but the distribution of thickness, the third major axis, is also reported. And they're in the size order that would be expected. Length, the black curve, is largest, width in green is second largest, and thickness in red is smallest of the three major axis dimensions. The window in the lower left allows the user to select different parameters to report, and the user selectable summary data are displayed in the lower right. These are the results of the PartAn 3D analysis for flakiness index. The table on the left lists columns of the screen designations and the size in millimeters of the square-holed screens used in the first screening operation. And the third column lists the rod sieve sizes in millimeters. All results are given in the table to the right. Square-holed screen designations are listed in the first column below a stay value, which indicates percent by volume in those size fractions. The pass column to the right is the list of percent passing the rod screen from the stay screen. The flakiness column then lists the flakiness index for each fraction and for the total sample at the bottom. Flakiness index is the pass value divided by the stay value as a percentage. Here's a view of a measurement result of flat elongated analysis displayed on the XY graph and table. Following the numbers on the graph, number 1 is a cumulative percent finer plot in a dashed black curve, which is the actual sieve data size distribution. 2, the red curve, is the PartAn calculated sieve data. 3 is PartAn width, 4 is PartAn thickness, 5 is the 1:3 length to thickness ratio, and 6 is the 1:5 length to thickness ratio, both as a percentage of the total sample. Any ratio can be chosen and reported: length over width, width over thickness, and length over thickness. On the table to the right, columns 4 and 5 display these two length over thickness ratio percent by size fraction. Any ratio can be chosen, including the sometimes used 1:2 ratio. This is a slide showing a scatter diagram display of the results. A three-dimensional surface roughness parameter, along with a 3D size parameter, width in this case. Any of PartAn's 36 parameters can be plotted relative to each other on this graph. The roughness parameters available are convexity, solidity, and concavity. For aggregate samples, these are all very similar in value, and any one can be used. The 3D width is shown in the top red volume distribution, which can be reported also in number. Convexity is reported on the right side red distribution on a scale of 0 to 1, 1 being a completely smooth convex surface. The summary data for each parameter are shown in percentiles, means, relative standard deviations, and number of particles on the list to the far right. Nearly 4,000 particles were measured in this small sample in less than 5 minutes, with complete data for all 36 parameters available immediately. This is the scatter diagram display of 3D surface area on the y-axis plotted against 3D thickness. The mean 3D surface area is 617 square millimeters versus a mean 3D thickness of 9.5 millimeters. This is a scatter diagram result of angularity plotted versus surface roughness, which is convexity on the x-axis volume distribution. Angularity in the y-axis runs from about 15 to 21. The higher the number, the more angular. Convexity goes from about 0.92 to over 0.99. 1 indicates an entirely smooth convex surface. And all summary data for both parameters are listed on the right, and the over 3,800 particles reported here were measured in 3.5 minutes. This is the PartAn 3D View Particles display, where the entire image file can be viewed, sorted by any parameter, C1 above, searched to isolate different classes of particles, C2 above, and display all 2D and 3D parameters for a selected particle in the upper right table. All images in the file can be viewed by scrolling and printed if desired. The images can be seen to have reasonably low surface roughness and low angularity, but very good unidimensional shape for strong load-bearing strength. Microtrac offers 4 different 3D automated image analyzers, all shown in this slide. At the bottom of the slide, the 2 different size ranges are given for the PartAn 3D series and the PartAn 3D Maxi series. 35 microns to 35 millimeters and 0.28 millimeters to 127 millimeters respectively. Both models come in online process versions and in lab versions. The upper left photo shows the PartAn 3D Pro, Pro for online process version, and it's shown here mounted on a pipe, sampling and measuring the sample stream and returning it to the process. At lower left is the lab version. The upper right photo shows the PartAn 3D Maxi Pro, unmounted on a process stream, and below it the lab version. The online Pro versions provide continuous, unmanned operation and sample measurement with turnaround time averaging about 10 minutes, which greatly improves process control response time with the normal increase in both productivity and quality versus having to collect the samples manually, bring them to a lab, and then go through making the manual measurements. It's so labor-intensive, manual sampling and measurement intervals generally end up being measured in hours or days, not enough time to prevent the process from going out of control and possibly shutting down. Microtrac has over 40 online image analysis systems like these installed in various processes. In summary, all aggregate geometric parameters can be measured on the PartAn 3D line of Microtrac particle image analyzers. Representative aggregate samples can be taken online and reported within less than about 15 minutes, in contrast to the traditional manual testing sometimes taking up to 1 day. Online measurement enables rapid control response to stay within tight tolerance specifications, increased productivity, decreased process downtime, and faster process startup. Lab versions of these products are available for R&D applications.
Thank you for checking out our on-demand presentation. We hope you found the content valuable. The best way to learn about our accurate and reliable particle characterization solutions is to see them up close and personal. Please send an email to the address on the screen to set up a complimentary analysis or schedule a demo. For more information about our entire suite of particle characterization solutions, visit microtrac.com.